Ah, there we go.
Right.
So in 2019, this paper by Genova et al. Announced that it had observed thermal Hawking radiation from an analog black hole in a Bose-Einstein condensate. That was taken to be a concrete confirmation of the existence of analog Hawking radiation in analog black holes. But questions still remain about what this means for astrophysical black holes. So can we take an observation of an analog phenomenon to confirm the presence of the astrophysical phenomenon? If not, or if we can't do that yet, are these experiments still useful? And if so, in what sense? So those are the questions that this talk will be focused around today. After giving a bit of a background on analog gravity, what analog gravity is, and how it's kind of evolved as a field since its inception, I'll split the talk into two parts. So the first part will ask, can analog experiments confirm? And after arguing for a heavily qualified yes to that question, I'll move on to the second part, asking why else might these experiments be useful? So I'll give a kind of survey of some of the new experiments that have been emerging over the last few years. From that, I'll identify two new roles that I believe these experiments can play. They can detect general or generalized phenomena, and they can also be used for exploratory purposes. From there, I'll wrap up with an outlook, including some open questions and also some open challenges for this field. So to begin, what is analog gravity? I'm sure many of you are already familiar with this, but I'll give a brief overview to make sure that everyone's on the same page. So basically, usually when we have a system that we want to learn about, we would isolate that system in a lab and run an experiment, manipulate different features of our system to see how it responds in different conditions. But with some systems, like black holes, we're not able to do that. So black holes are unmanipulable, and many of their features, including Hawking radiation, are inaccessible, so we can't even detect them from a distance. So we're put in a position where one of the best things we can do is to try and learn from model black holes in the lab. And this idea was first introduced by Bill Unruh in 1981, who realized that there's an analogy between the flow of quanta of sound, phonons, in a flowing fluid, and the propagation of quantum fields on curved spacetime. So the heuristic of the analogy goes something like this. You can imagine you're a fish swimming with a friend in the river just above Niagara Falls, so in this nice calm area above Niagara Falls up here. And you're having a conversation with your friend, you're just floating along with the flow of the water. Meanwhile, the water you're floating in is moving faster and faster towards the waterfall in a certain direction. And then at one point, your friend decides to stop off in a pool on one of those islands up top, but you carry on moving with the flow of the fluid, and you're still trying to communicate. If the river is moving faster and faster and faster towards the waterfall, at some point you'll reach a point where you will no longer be able to communicate with your friend, because you'll be moving faster away from your friend with the flow of the river than your sound waves are able to move towards your friend. This is what they call an acoustic horizon. And the idea is that this acoustic horizon can act as the analog of the event horizon of an astrophysical black hole. So Unruh came up with this heuristic, but he also showed that it can be made mathematically precise to the point where we can actually identify an isomorphism between the mathematics describing the two systems. And based on that idea, he suggested we could use one system to learn about the other. Since then, these experiments have actually been done, leading to images like this one that you see on the right. So analog gravity as a field is a study of accessible non-gravitational source systems whose mathematical models are isomorphic to our best mathematical models of inaccessible gravitational target systems. And the field was originally focused on confirming the existence of astrophysical Hawking radiation in Schwarzschild black holes. The original focus of the field was really to build an analog black hole in order to confirm the presence of Hawking radiation in astrophysical black holes. The isomorphism that underwrote that initial focus was this isomorphism between the Schwarzschild metric and a metric describing the propagation of phonons in a flowing fluid, which you can see on the right-hand side here. How do you get to that isomorphism? Well, you clearly don't get it for free. You have to make several assumptions about the way that your fluid is behaving. So you have to assume that the evolution of the bulk fluid flow can be described by the evolution of two fields, the density field and the velocity field. You have to assume that your fluid is flux-free. You have to assume that the only forces present in the fluid are gravity and pressure. You have to assume that your fluid is irrotational, so that the velocity field can be written as the gradient of the scalar field. You have to assume that the density only depends on the pressure. You then have to make two linearity assumptions. So you have to assume that the speed of sound in your fluid is approximately constant. And you have to assume that excitations in your fluid can be accurately described as linear perturbations of the bulk fluid motion. If you have all of these assumptions in hand, then you can move on and generate your metric. You start with the continuity equation and Euler's equation, two fundamental equations from fluid dynamics. The continuity equation relies on the flux-free assumption I just mentioned, and the Euler equation relies on the adiabatic assumption. From there, you introduce perturbations, linear perturbations around some central solution. So you linearize and then you substitute those equations into the continuity and Euler equations. You solve them to first order. And from there, you extract a wave equation. And from that, you can extract your metric, which gives you the isomorphism that I showed a few slides ago. So that's how you get this isomorphism for looking at Hawking radiation in an analog Schwarzschild black hole. So this initial focus of the field can be broken into roughly into two eras. The first era was a theoretical era where the field didn't really have any viable experiments, and that ran from around 1981 to 2008.
Weren't the fish doing experiments?
Maybe. So in 1981, that was when Unruh published his paper, Experimental Black Hole Evaporation. That was where he first introduced this idea. Then between 1981 and 2008, which was really a long time, so a couple decades of work, the field remained mostly a theory field, and the theory of analog gravity was expanded and developed. So papers were showing how to define and identify other features of black holes in an analog system, including the ergosphere, trapped regions, the acoustic apparent horizon, and the acoustic event horizon. Other papers were suggesting experimental protocols, so suggesting ways that this idea, which was just a theoretical idea, could actually be made experimentally viable. In 2002, in particular, Schutzold and Unruh were the first to suggest using surface gravity waves as an experimental protocol. So that protocol, instead of using sound waves, it uses surface gravity wave disturbances in a water tank, essentially. And that proposal led to the beginning of the experimental era, which started in 2008. The first experiment was one of those surface gravity wave experiments. So Russo et al. Showed the conversion of positive frequency to negative frequency modes in a surface gravity wave analog white hole. So they weren't dealing even with an analog black hole at this stage, they were dealing with the time reverse of an analog black hole. This was more of a proof of concept to show that they could produce something that looked like an analog horizon. And then the experiments developed from there. So in 2010, you have other experimental protocols becoming viable, including bulk crystals and Bose-Einstein condensates. In 2011, the Nottingham group observed the excitation spectrum for surface gravity waves scattering off of an effective white hole horizon. And they saw that that spectrum agreed with Hawking's predictions. Then finally, in 2016, two papers report that they've observed the correlations between positive and negative modes thought to be an essential feature of the Hawking effect. And this was viewed as the first observation of analog Hawking radiation. Since then, that result has been reinforced and made more precise in further experiments, leading to that 2019 result that I started. Yes?
Just to make sure that I understand.
Mm-hmm.
So this Hawking radiation that you mentioned,
Mm-hmm.
usually think of Hawking radiation as a quantum gravitational effect,
Mm-hmm.
but this seems to be at the classical level, at least the analog between the two methods seems like.
Mm-hmm.
So maybe could you explain what is Hawking radiation that you're looking for?
Yeah, so great question. So some of these experiments were purely showing the classical effect, and then some of them in Bose-Einstein condensates were showing the quantum effect. So that was why these 2016 experiments, which were on BECs, were thought to be a kind of distinctive result because they were claiming to show the quantum effect.
Thanks.
So it seems clear that analog Hawking radiation has been observed, but then the next big question clearly is, what can these analog experiments tell us about the astrophysical case? Can analog experiments in principle confirm hypotheses that we have about their target systems?
So
Mhm.
would you say these experiments also confirm that information is destroyed?
That's a whole other question.
No, it's not a whole other question. So Hawking radiation, one of its important properties is that it's incoherent,
Mhm.
that the late time and the early time are not. That's one of its really most noticeable features.
Mhm. Mhm.
And many people believe that that's not true of the actual
Mhm.
radiation.
Mhm.
So
that's one of the things that the experimentalists are actually trying to get out of these experiments is ideas for how information could be preserved and that sort of thing. But it's highly controversial, and whether you could transfer those conclusions from the analog system to the astrophysical system is part of the controversy as well.
right, but if you're claiming you're learning something about astrophysical black holes, you're saying that you're throwing out the ones that you want to believe and you don't want to believe and keeping the ones you do want to believe?
No, I'm not saying we're necessarily learning anything about the astrophysical case yet.
Oh, I thought that's what you did.
I'm asking, for now, I'm just asking the question, and then I'm going to argue for an answer to that question.
Well, you told us the answer was going to be yes.
It's going to be a qualified yes. So we'll get there. So for now, what are we even asking when we're asking, can analog experiments confirm hypotheses about their target systems? Well, you can label our mathematical models of the two systems as MS and MT. And these are the models which we believe adequately describe our two systems, S and T. So MT is the model that predicts the target phenomenon that we're interested in. So for example, Hawking radiation. And then MS is going to predict its analog. So analog Hawking radiation, for example. Based on similarity between those two mathematical models, we want to infer that evidence that we gather in support of MS doubles as evidence in support of MT. And to be even more precise, what we want to do there is to extract a result where the probability of MT being an adequate model of T, given the evidence collected from the source system E, is greater than the probability of MT being an adequate model of T on its own. So that's what we are trying to get at when we're saying we're aiming to confirm hypotheses about the target system using evidence collected from the source. So unsurprisingly, this has been highly controversial, and in particular, several authors in the philosophy literature have highlighted a circularity concern with this goal to confirm hypotheses about the target system. You can get at that circularity concern by looking at the reasoning underlying this analogical reasoning and breaking it down into three layers. So at the top layer, we have the systems themselves, S and T. I'm going to put a cross on the arrow between them here because that's not where the analogy lies. So we're dealing with, say, a water tank on one hand and an astrophysical black hole on the other. They're very different systems existing at very different scales. We wouldn't normally class them as the same type of physical system. Where we have the connection is at the next level, at the level of the mathematical models that we believe adequately describe those systems. But then if you dig one level deeper, you have to think about what conditions actually need to be satisfied in order for our beliefs about the adequacy of those models to be correct. So what are the conditions CS that need to be satisfied for MS to in fact be an adequate description of S? And what are the conditions that actually need to be satisfied for MT to be an adequate model of T? And at face value, given everything I've told you so far, we don't know if there's any additional connection there. So the only level that we have a connection at is the level of these mathematical models that we believe to be adequate descriptions of the two systems. That leads to a circularity concern. So if the similarity between MS and MT is the only connection between the source and target systems, how can we use evidence from the source system to confirm MT's adequacy as a model of T? Wouldn't that force us to assume the very claim that we are trying to test? So if the only connection we have is based on our belief that MT is an adequate model of T, how can we then use that connection to confirm MT's adequacy as a model of T? That's the basic circularity concern here. So it has been controversial in both the physics and philosophy literatures, but some resolutions have been proposed, and I want to argue that this circularity concern can be resolved in principle, although in practice it's hard to satisfy the conditions for solving. So just to get clearer on what the concern is, you can represent the variables at play here as Bayesian variables. So you can draw a Bayesian diagram here. The nodes here just represent variables which can either take a positive or negative value. So the node for MS is going to take a positive value if our belief that MS is an adequate description of S is true, and a negative value otherwise. The node MT similarly will take a positive value if our belief that MT is an adequate description of T is true, a negative value otherwise. Then I've introduced this other variable E here that represents the evidence collected from the source system. So that will take a positive value if the evidence we collect from the source system does support the adequacy of MS as a model of S. The arrow here indicates the connections of probabilistic dependence. So the arrow here indicates that we're more likely to collect evidence in support of MS if MS is indeed an adequate description of the source system. So because of the circularity concern, the worry here is that we don't have a probabilistic connection here between the values of MS and MT, and that's what we would be looking for in order to actually be able to gain confirmation of this node based on a change in the value of this one. So we basically need some kind of bridge to connect these two nodes here.
Yeah.
Mm-hmm.
So so in the experiments that have been addressing the circularity thing,
Mm-hmm.
and in the experiments that have been done,
Mm-hmm.
the information is not coming out, it's literally going down the drain. You can see it during one thing. Your retort to that was experimentalists are looking for experiments in which it comes back out. So if you're looking for experiments that will confirm what you think is true, how can one, that seems completely circular. And
Well, they're not exactly looking to confirm that claim. They're more investigating the different kinds of mechanisms by which Hawking radiation can be produced in an analog sense. But we'll get to that idea in a bit. Because so that work is more, I believe, on an exploratory angle rather than a confirmatory angle.
But doesn't that show that you can't learn anything new about if you're changing your experiment when it disagrees with the conclusion you're expecting?
Oh, only if your goal is to confirm a very particular hypothesis,
Yeah.
and then you keep tweaking your experiment until you get a confirmation, then
Yeah.
yes, I totally agree. But a lot of these experiments are they're not anymore trying to confirm a particular hypothesis. And that's one of the main trends that this field is moving towards, which I'll say more about in a bit.
So presumably the one who has used these experiments to argue that information is destroyed.
I don't actually,
believes that.
I'm not 100% on exactly what his line is on the relation between information loss and these experiments. So for now, I'll just carry on with this, and then hopefully that will become a bit more clear later on. So Dardaschi et al. In 2019, they introduced exactly this kind of bridge between those two Bayesian variables that you would need to connect the evidence E with our claim about the target system MT. In particular, they suggested that if we introduce an independently plausible universality argument, which, if confirmed, would support the adequacy of both MS and MT, then that universality argument can play the role of this X variable here. And you can see that it forms a bridge between MS and MT, thereby connecting E with MT. And that gives us the probabilistic dependence that we're looking for. So what kind of thing is this universality argument? It's essentially any kind of independently plausible argument that tells us to expect some macro phenomenon, for example, Hawking radiation, to be resistant to certain changes in microphysics. So it's a kind of argument that tells us to expect these two systems, one being an analog system and one being an astrophysical system, to both exhibit Hawking radiation, regardless of details of their microphysics that are different, and in particular, regardless of details of their microphysics that we might be worried about undermining Hawking's original prediction. That's the kind of argument we're looking at here. The general structure of that argument is something like all systems whose microphysics have certain features K1 through Kn should exhibit macro phenomenon Q, regardless of their other microfeatures K1 primed through Km primed. So then in a bit more detail, the mechanism by which this universality argument helps us runs as follows. If we collect evidence in support of MS from the source system, that evidence confirms the adequacy of MS as a description of S. That's just a standard experimental result. But if we have one of these universality arguments to hand, we can say that that evidence also confirms our universality argument, which predicted that MS would be an adequate description of S. But that in turn confirms what our universality argument has to say about MT, namely that MT will be an adequate description of T. And this is how universality arguments can facilitate confirmation of target hypotheses by evidence collected from an analog source. This has also not been entirely accepted in the literature. So Crowther et al., for example, have taken issue with drawing the arrow between X and MT at all, arguing that that presupposes probabilistically what we would like to establish. But I think it's fairly clear that the conditions that we have to set ourselves in order to build this Bayesian diagram are actually very weak. So we just need to assign some very small likelihood to the probability that our universality argument will be positively relevant to the adequacy of our target model. Yes?
I am more worried about the arrow from X to MS.
Okay.
Because you're not trying to reverse it, right? Your original argument went this way down from X to MS, and then you said E is going to check whether connection is good or not. But now you're then pushing it back and saying, if I have verified this connection, then my original X has to be true. And therefore MT is to be true. It's not obvious to me that logic permits you to reverse the.
I see what you're saying, yeah. So maybe the heuristic kind of step-by-step mechanism was a bit too far, a bit too quick that I gave. But if you run through the Bayesian probabilities that are provided by this diagram, you do end up getting that you can extract confirmation out of it.
Wait, and Crowder's point is the same as what Andy just raised, right?
They're concerned about drawing this arrow here. So their concern is
Is the
essentially,
presupposition about
it's the presupposition that we have a universality argument, which is actually relevant to our hypothesis about the target system. That's what they're concerned about. But just by drawing this arrow, we just need to, all we're doing is assuming that there's some very, very, very small increase in probability of our hypothesis about the target system being correct, given that our universality argument is correct. It could be infinitesimally small. So this diagram really isn't assuming very much. So I would take issue with Crowther et al.'s criticism there. This argument seems to, it does stand, and it does allow us to at least envision how we could get confirmation out of these experiments. But what we do need to worry about, I want to argue, is the strength of these arrows connecting X with MS and MT. If that connection isn't strong, so if we are only dealing with some infinitesimally small difference in probability, then the confirmation we're going to get out of our experiment for our hypothesis about the target system is also going to be very small to the point that it will be more or less insignificant. And you can see that by looking at this expression for the degree of confirmation that you can get out of these experiments. So delta C here, that's the degree of confirmation. So that's the difference between these two probabilities. You can see that delta C is a function of 4 factors. You have this first factor, which has to do with the probability of our universality argument holding true and the probability of us collecting supportive evidence from the source system. But more importantly, the confirmation that we can get out of our analog experiment is directly a function of these 3 factors: delta S, delta T, and delta E. Delta S corresponds to essentially the strength of the connection between X and MS. So how relevant is our universality argument to our hypothesis about the source system? Delta T corresponds to the strength of the arrow between X and MT. And delta E corresponds to the strength of the arrow between MS and E. This means that analog experiments can, in principle, provide significant confirmation for hypotheses about their target systems, but only if we're confident that the source and target systems do indeed have the microfeatures K1 through Kn invoked by our independently plausible universality argument. So only if the values of delta S and delta T are significant.
So there's a possibility that, if I understand correctly, there's a possibility they could have multiple universality arguments, but you need to like figure out what's the correct one for which both theories share common, I guess, traits.
Yeah, you could have a whole array of universality arguments, but so the goal, if you want to get maximum justification for saying that you've confirmed your hypothesis about the target system, would be to pick the universality argument that maximizes that delta C function there. And that's going to be one which invokes features that we're very confident that the source and target system both have. Does that make sense? So that's the sense in which I want to say, in principle, analog experiments can confirm hypotheses about their target systems. But whether or not we're in that position with respect to analog black holes is another question. And given our current knowledge of the microstructure of quantum gravity, and given the universality arguments that we currently have available, we're not in that position for analog black holes and for Hawking radiation.
Sorry, this is the side. So from the
Yeah.
Bayesian approach, you should also be able to run with universality arguments as well, right?
Based on the degree of confirmation that they would
Yeah.
give you. Sure, yeah. Was there another question? Oh, no. Good, so I want to say that existing analog black hole experiments are not able to provide significant confirmation for the presence of astrophysical Hawking radiation, even though in principle, analog experiments should be able to confirm hypotheses about their target system.
So
Mhm.
the significance depends on the weaker of the two connections between X and MT or MS. Is that right? Is it a multiplicative term?
Exactly. So it's actually possible to show that each, if you consider this first factor to call it gamma, for example, it's possible to show that each of those 4 factors is bounded above under reasonable conditions.
Mhm.
So if any one of them is very, very small, then your degree of confirmation that you get out is also going to be very, very small. You're not going to end up in a situation where one of them being absolutely huge will outweigh the fact that another one is infinitesimally small. So each of them has to be significant in order for your degree of confirmation to be significant.
And delta T is the one that we think is most likely to be quite small.
Exactly.
And
So on this basis, it seems that analog black hole experiments have limited usefulness, at least right now, if all we can get them to do is to try to confirm hypotheses about the target systems. And that brings us to part 2. So why else might these experiments be useful? So since 2017, these are all kind of rough chunks of time, but roughly since around 2017, there seems to have been a new wave of experiments that are involving new media and trying to do new things for new reasons. And the physicists themselves seem to have acknowledged that they've kind of entered a new phase in the field. So this is a quote from a special issue in 2020 titled "The Next Generation of Analog Gravity Experiments," which was following on from a conference of the same name, where a variety of experimentalists and theorists were describing new experiments and new trends in the field. And the quote goes, "Over the last few years, a new wave of experiments have appeared, facing different challenges and attempting to extend the analogy beyond the observation of the Hawking effect in the laboratory." One of the new trends that you see is 1+1 dimensional analog black hole experiments in new media. So the first kind of the initial focus of the field was predominantly dealing with 1+1 dimensional analog black hole experiments in surface gravity wave experiments and also Bose-Einstein condensates. But from 2017 onwards, you see the first observation of stimulated Hawking radiation in an optical analog. You also see the first effective analog white hole horizon in superfluid helium. And you see, for example, a new proposal for an experimental protocol, flowing films of soap, and a description of how that protocol could also support an analog horizon. You also see analog gravity. Yeah.
Sorry, could you describe what you mean by an optical analog?
An optical analog. So essentially, the idea is the same. They're just using light instead of a kind of water and surface gravity waves. I could explain in a bit more detail if we have time at the end, or send you some references. But the idea is the same. You're just using different media, and different media are kind of tunable in different ways. So they'll be able to. So the optical analogs are especially useful for particular features that you're trying to look for example. So you also see a shift towards rotating black holes as well, which also means a shift away from just looking at the production of Hawking radiation. So you see this paper, which observes superradiance in an analog rotating black hole. You also see an optical version of an analog rotating black hole. You see an analog Kerr black hole. This paper produces an analog Kerr black hole and then does a bit of a compare and contrast between what they see in the analog and what they would expect to see in the astrophysical case. And then you see papers like this, which are also about superradiance. This one in particular focuses on the first paper I'd put up here, but focuses in on the ways in which the experimental regime actually differed from the regime in which superradiance was predicted. Then going even further, you see experiments that aren't even about black holes at all, and instead are trying to model whole universe effects. So you have an experiment using a rapidly expanding Bose-Einstein condensate ring to model an expanding universe. You see phonon pair creation by inflating quantum fluctuations in an ion trap, so as the analog of cosmological pair creation. And you see experiments looking at vacuum decay, for example. So these new experiments, they aren't only focused on Hawking radiation, and they aren't only focused on black holes either. What makes them even more interesting, I believe, is that they're also focused on new goals. So they're no longer just trying to confirm hypotheses about their target systems. And there's two new goals that I think have really come to the fore here. The first one is detection of general or generalized phenomena. So as analog gravity as a field has developed, there's been a shift away from thinking of astrophysical Hawking radiation as the true instantiation of Hawking radiation towards thinking of the Hawking process as a much more general phenomenon that could have been discovered in any number of systems, but just happened to be predicted in an astrophysical system first.
And then studied analog and this. Actually study based off of that universality argument.
Analog experiments can start to play, as shown by these new experiments that we're seeing emerging post 2017. The second new role is an exploratory one. So we can use the analog system to explore instead of having a hypothesis that we're trying to use it to directly test. So in particular, in some of the recent experiments, you see these sorts of questions. How do analog gravity systems behave under different conditions? So how do systems evolve? How do processes unfold? You can see an example of this sort of open-ended exploration in this book. Spontaneous Hawking radiation in analog black holes was suggested, developed theoretically, and observed. Here we repeat the observation at various times and follow the time evolution of Hawking radiation in an analog black hole. We compare and contrast the evolution with the predictions for real black holes. So you can see here, it doesn't seem as if this investigation was trying to test a particular hypothesis about the source system or the target system. It was using the black hole to see how processes unfolded over time. Another kind of exploration you might have is more like this other question on the right-hand side. Under what conditions will a predicted analog gravity phenomenon appear? So what happens if we violate idealizations in our predictions of a certain phenomenon? What if we enter a regime we don't understand theoretically? Will this phenomenon still appear? You can see that in this Torres 2020 paper. So it's known that this analogy holds only under specific conditions, which were not all satisfied in this experiment. The deviations from the analog regime was further development of our concepts to new regimes, which deepened our understanding of various processes such as superradiance or vortex relaxation. So for this kind of exploration, you can think back to those conditions that we had to satisfy in order to set up our isomorphism at the start. What's happening in a lot of the experiments is that some of those conditions actually are very difficult to satisfy and aren't being satisfied in the experiments, but you're still seeing the same phenomenon here, or sometimes interesting new phenomenon that you haven't predicted. And that's this kind of exploration of robustness that those experiments. You also see the first kind of open-ended exploration in experiments on cosmological redshift and Hubble friction in an expanding BBC, on acoustic rotating black holes, and on cosmological pair creation. And you see the second kind of exploration of robustness in experiments on Hawking pair production in optical analogs and in other emerging research programs. And again, I think these roles can be generalized. So analog experiments, even beyond these analog gravity experiments, can play a role as open-ended exploratory tools. They can allow us to look at the analog system to see what we find and ask questions like, what would happen if? And by doing that, we can generate ideas, which might then allow us to develop our theory further and prompt new experiments. They can also play this exploration of robustness role. So by taking predicted phenomena beyond the regime in which they were predicted, we can ask what would happen to this phenomenon if we did X, if we did Y, if we did Z. We can then kind of push the boundaries of what our theory has predicted, and again, push ourselves in new directions to ask new questions. So those are the two new roles that I think analog experiments can play. And those are the new roles that are supported by this new wave of analog gravity experiments that we see. They lead to a couple positive implications for analog gravity as a field. So you can have overlapping goals. As I've already mentioned, you can have
You can have exploration that leads to generalization. So by exploring a phenomenon in your analog system, that might prompt you to discover that the phenomenon is actually more general than you thought, or that it actually exists outside the idealized regime in which it was originally predicted. So those two roles can play into each other in a positive way. You can also have an experiment that overlaps in another sense. You can have an experiment that started off as a traditional experiment, which did aim to confirm a hypothesis about this target system, but then ended up leading to exploratory conclusions and playing an exploratory function. As with all exploratory experiments, these exploratory experiments lead to unexpected applications, unexpected results, and technological advances. These new experiments can also lead to reinterpretation of past results and redirection of research. So some of these experiments, or in recent years, some of the original analog gravity experiments have actually been reinterpreted in light of this new focus on robustness. So entire papers have been published focusing just on how the original experiments actually deviated from some of those assumptions I went through at the beginning, and explaining in what sense that teaches us about the phenomenon that we're looking at. By exploring, you're also building up a bank of possible scenarios. So you're able to kind of look at what the target system might look like if it had certain features or if it had certain other features, which means that eventually if we did end up in a position where we could transfer confirmation to the target system, we would have a lot of scenarios that we can draw from to do that. Importantly, it can point the theory in new directions by again asking targeted questions that theorists might not have otherwise thought to look into. And on some level, these new roles avoid the controversy of the original confirmatory role, because again, they're not trying to just confirm a hypothesis about the target system. Their goals are a lot more broad and wide-ranging. There are, however, some significant challenges, I think some fair, open, challenging questions for this field from both a philosophical and kind of physics angle. So are these goals that I've highlighted really new? That's a fair question. There have been different streams of research that have been evolving with the field since it was first founded in 1981, and they have been playing into each other throughout that time. What I've identified is just some bulk trends that seem to have emerged, but I think it's fair to say that some of the authors were already thinking about using these experiments for different purposes, even back in 80s and 90s. Would these experiments be valued if not for the analogy? I think that's a very interesting and open question. How can we make precise the idea that generalization isn't just about semantics? That's a more philosophy-oriented question, but that's a difficult question and an important one, and that relates a bit to the question that was just asked earlier about what the role of this universality argument is in other experiments. Are exploratory analog experiments more like simulations than experiments? That's also, are our goals in doing these exploratory experiments more like our goals in running a computer simulation, for example? Why is exploring analog systems as opposed to other systems especially important or useful? Are the new experiments still analog in any meaningful sense? So if we're not able to immediately draw conclusions about the target system, what role is the analogy even playing? At what point might a transfer of confirmation from the source system to the target system become possible? And finally, will these experiments lead to significant theoretical developments for the target system? That last question is an open question, but recently, I think that there's been a promising example of work that leads in that direction. So a recent paper predicts the analog Hawking spectrum that we would expect with an unexpected peak corresponding to a quasi-normal mode. The frequency of that mode is determined by the standard macroscopic features of a black hole that we're all used to, but the mechanism by which it's produced is quantum. And the authors of that paper are currently in conversation or looking to be in conversation with gravity theorists to see if we could expect to find similar results. This is, in the author's own eyes at least, the first time that analog gravity has predicted a new effect. So it also marks a kind of a new phase for analog gravity as a field. And I think that's a promising note to end on. It's not a guarantee that confirmation will be possible, but it points us in a promising direction. Thank you very much, and I hope there's still a bit of time for questions.
Thank you, Grace. Questions? Yes.
There's like, so with respect to the universality argument, there's like, I guess, gaining constraints on the correctness of the universality argument require your ability to evaluate the target system. Because it seems like to me without that, you can only really say statements about the theories themselves, not really the target system.
Mhm.
System.
Yeah, so you're asking how could we get confidence that a universality argument is relevant to the target system without having access to the target
Because we
system?
don't even know if the theory is relevant to the target system, right?
Yeah, so let me go.
I guess it's a good example. Or so before Nicholson Morley, people thought there was like an ether, and there is a universality argument that always propagates through an ether. And even though light obeyed the theory of wave mechanics from the experiment, that universality argument is just not relevant for light.
Yeah.
It seems like it would be hard to evaluate. Use it to figure out whether universality argument is even relevant to the target system. Or that seems like an example where even though the theory is relevant, the universality argument is not. So and I see like it'd be hard to do that without actually evaluating the target system.
Yeah, definitely. So this is definitely one of the challenges for analog black hole experiments in particular, is that we don't even have enough access to kind of gain confidence that the analog black hole, or sorry, that the astrophysical black hole will actually have those kind of key features invoked by a universality argument. I think there's kind of two things going on here. I think in one sense, there's always going to be a risk that the category that you've placed your systems in actually isn't a good category. And that's a risk with even a very everyday kind of standard experiment on 2 electrons, for example. So you're always making some assumption there that you can actually place those 2 systems into the same category. So what we should be doing here is not to try to eliminate that risk entirely, right? But to place ourselves in a similar kind of position to what we would be in a kind of everyday lab experiment. And I totally agree that I think in practice, given what we know now about black holes, it seems unlikely that any universality argument could come up where we would be able to say, yes, we're very confident that astrophysical black holes have those features A, B, C that the argument invokes. The kind of argument that we'd be looking at, so the strongest universality argument for Hawking radiation that's been produced so far is by Unruh and Schutzold, and it modifies the dispersion relation. So that's meant to model all possible quantum gravity effects as modifications of the dispersion relation. And it shows that subject to 3 assumptions or 3 constraints on how the dispersion relation is modified, you will still get Hawking radiation out as Hawking predicted. The problem is that we are not confident that actual astrophysical black holes satisfy those 3 assumptions. So the issue is exactly what you've identified in practice. Yeah.
So good question. Having to do with the arrows that I think people were talking about before.
Yeah.
So when I think about universality and signatures, I think of these photon rings that some people here have been working on, namely multiple orbits around the black hole. So if we go the other way, you could say there's a prediction from this theory of black holes, and you see that manifest in optical analog, the fluid analog. So when you see multiple orbits of phenomenon around the analog, and they show the same ratios between intensity, but they show the same thinness, shape, geometry, morphology that you would expect from light orbiting a black hole. Have these kinds of experiments been done? So you better validate trace through that diagram?
So they're actually just getting there. So I was just talking to an experimentalist the other day, who was talking about the photon orbit and how an experiment has just recently been done of kind of getting close to that. We're not quite there yet, but the idea is that the field is kind of catching up to get to a point where it might be able to sort of make those kinds of.
Last question, yeah.
I wondered if there was a slightly different way to think about it when even setting up the analog systems.
Right.
So depending on the feature of the theoretical prediction that you want to test, would it be useful to think of a minimal set of features that you have, the analog system has to have before it can even test or push to give you anything new? I'm just wondering, because there are these sort of two domains, right? There's like the classical kind of, there are essential features of black holes that any analog experiment has to reproduce before it can actually even be an analog
Of a black hole.
Is that one way? Is that a useful way to think about it at all, or is it not?
Yeah, I think it definitely is. I think it's quite similar to this universality argument frame, actually, because those features that you just mentioned, you could just treat those as the features that you need your universality argument to invoke. So I think it's the same kind of idea.
The what is different about doing it this way is that you can then pick and choose on what phenomenon you want to reproduce, right? So if it's Hawking radiation or a photon ray, then the features that need to be reproduced are slightly different. In the analog system.
So I think that's exactly what people have in mind with the universality argument.
So in this language, all the old experiments, I think, the only requirement they had was there should be a horizon.
Right.
Right?
That's right.
If I have a horizon,
So that's a minimal set.
that's the minimal set. That's the first thing I need. Then I can do all these experiments. Now you're asking, can we now put additional K2, K3, K4, and
more
then
more
say,
features.
So totally. I definitely think it wouldn't be good to get into a mode of thinking where you're just thinking of these systems as analogs of black holes in all senses of black holes, so again, it depends on your goals. Whether a system counts as a good analog is going to depend on what you're trying to get out of it. And you might only need one or two features if you're interested in seeing.
Right. So the robustness then becomes, you have multiple levels of robustness.
Yeah.
Right. So depending on.
Exactly. Yeah. Thank you.
Did you have a question?
Mine's more of a conversation, so let's all get to lunch and talk about.
I was gonna ask, I'm sorry, I asked many questions. Yeah, I was gonna ask when you say it's like these analog systems are better at making more robust statements about this, the general feature of Hawking radiation regardless, rather than particularly about black holes. Since we're unable to really construct such a universality argument.
Yeah, definitely. So there's particular concerns about the astrophysical Hawking effect, right? Namely the transplankton problem. And it's unclear whether analog black holes are able to say anything about that. I think it's probably clear that they're not. So if that is your particular concern about astrophysical Hawking radiation, then yes, these experiments aren't going to be able to help you very much. But if you are interested in the general Hawking process, and consider observations of analog Hawking radiations to be genuine detection of that general Hawking process, then it can teach you a lot about how that general process behaves in different conditions.
A very last question for Andy.
I wonder if you could comment on the following, generally related to what you've been. So you've been discussing what scientists sort of logically ought to conclude from the experimental life. And then there's which is often very different from what they actually do conclude. And two things which have always puzzled me, examples in this regard, is first of all, the existence of black holes themselves.
Mhm.
Which, when I was a graduate student, people in particle just really didn't believe in it.
Yeah.
And amazingly, and I don't think the final inverse of doubt work extinguished it till these guys took the picture. Well, it's, I don't think they're free. Now, you could attribute that to, I'm a scientist, I don't believe it until I see it.
Mhm.
But then the opposite example is, I think, is actually Hawking radiation. I have never heard anybody say, it's not measured, we're not going to measure it. I don't think I've ever heard, I'm sure it's been said, but I personally have never heard anybody say, I don't believe Hawking radiation exists. Have you said it, Dinesh?
I said it to you once and you said, you're the first guy who ever said it to me.
That was one. Okay, there was one.
And then one.
Okay. Sorry.
But I don't talk, I'm not a particle physicist.
I thought you were joking. So I don't really understand that, and I don't understand the black. Do your intellectual adventures shed any light on this? Do you want me to peek at?
I mean, that has come up in the literature as well, how everyone believes in Hawking radiation, but it's sort of remarkable. There's definitely some people who've argued as a basis for kind of underwriting the importance of these experiments, that it's remarkable why everyone believes in Hawking radiation, and they actually shouldn't be as
Come on,
confident
Grace, share
as
your
they are.
opinion.
Well, if people were more skeptical of it, these experiments might have had more
Yeah.
Yeah.
impact,
Yeah,
but nobody needed to be.
nobody needed to be convinced.
Yeah.
Um,
Except for Ramesh. Ramesh, are you convinced now?
I say shame on the physicist. I mean, just swallowing it whole just because it came out of an equation.
It seems like people get that confidence from different sources as well, though, which is interesting. But yeah, I don't have strong opinions.
All right, I think we can leave it at that. Thank you.
Thank you.
We now have a luncheon party.